Hi everyone! The goal of this video is to learn how to apply the idea of similarity. So we're going to use what similarity means to solve some algebraic or just straight calculation problems. So we're going to start with some DERA problems. So remember DERA, D-E-R-A. D stands for diagram, which you may have to draw or it may be drawn for you. E is equation, R is reason, which is really important and we'll talk about, and A is answer. So what we are given is that triangle ABC, squiggly line to triangle DEF. So that squiggly line again means the triangles are similar. So again, what similar means is that they're going to be the same shape but different sizes. So that means they have the same exact angles, but the side lengths are going to be different. So when you're approaching this problem, that's going to ask you to find the side length AC. I always want you to start by giving me a nice diagram of what's going on so you can visualize. A lot of geometry is visualizing. So I'm just going to label this triangle ABC. I don't care how you label it, I just went around. The only thing that matters is that the corresponding parts line up. So A and D should be in the same place. So D should go right here. B and E should be in the same place, so if B is up here, E will be up here. And C and F will be in the same place. Keep in mind if those were rotated, you'd have to think a little bit, but they're facing the same way, so you can just label them. Okay, so now it gives you a bunch of side lengths. So AB is the length from here to here is x plus 1. So get a nice diagram going on here. AC is x plus 6. DE is 32. And DF is 48. And the goal is to find the length of AC. So let's think about what that means. AC is this line here. Well, we know it's x plus 6, but is that the length of it? No, that's just the equation that represents the length. So in order to find what the actual length is, we're going to have to figure out what x is. So we can plug x in and calculate the length. And in order to figure out what x is, we're going to need to probably use the idea that these triangles are similar. So what we know about similar shapes is they do not have the exact same side lengths. So I cannot say, and I'm going to emphasize this because it's important and people will do this, x plus 1 equals 32. Are these side lengths equal? Just look at them. No, similar shapes are not equal side lengths, so you cannot do that. So please do not do that. I'm saying this 500 times so you don't forget. Okay, what we do know about the side lengths is that the ratios are the same. So the scale factor to go from this side to this side should be the same as the scale factor to go from this side to this side. Now I'm going back and forth between the word scale factor and ratio because a ratio is just writing these as division. So like the ratio would be like AB over DE, which is essentially the same thing as calculating a scale factor, because to calculate a scale factor, you're just going to divide the side lengths. So the ratio to go from AB to DE, we can write as AB divided by DE. That's the ratio. It's the same thing as calculating the scale factor, but I haven't substituted numbers. And the ratio to go from this side to this side should be the same as the ratio to go from this side to this side. The important thing is to keep this consistent. So I go from big triangle to the corresponding side of the small triangle. So that should be the same as this corresponding side to this corresponding side. So I got to start with the big triangle, which is AC. Should have the same ratio or scale factor as the sides over here, but the corresponding side to AC is DF. So these ratios should be equal because they have the same scale factor, and really these compute the scale factor. So let's go ahead and plug in the numbers that we know. So AB is x plus 1, DE is 32, AC is x plus 6, DF is 48. So big triangle, small triangle, big triangle, small triangle. I have corresponding sides matched up together. So I know I set up this proportion correct. Keep in mind our goal is to solve for x because we want to find AC. In order to find AC, we have to substitute something in for x. So to solve for x in this, we have a ratio equals another ratio, and the only method to solve that is to cross multiply. Okay, so in order to cross multiply, you're going to multiply all of this by all of this. So I'm going to take 48 and multiply it by all of x plus 1. The reason I keep saying all is because you're going to have to distribute. I'm going to take 32 and multiply it by all of the x plus 6, the whole side, not just the x. So I'm going to have to distribute the 48 out, and I'm going to have to distribute the 32 out. So 48 times x is 48x. 48 times 1 is 48. So you see I had to scale both the x and the 1, or multiply them both, not just the x. Okay, 32 times x will give me 32x, and 32 times 6 will give me 192. And now I can just solve this equation for x. So I'm going to pause the video. I want you to go ahead and solve now that I've done the distributing and see what you get. Okay, I hope you tried solving this on your own. I first combined my x's, I then combined my numbers, so I subtracted 32x, then I subtracted 48 from both sides, and I ultimately got that x equals 9. Okay, so is this my final answer? Let's go back to the original problem. The problem asks you to find AC. Have I done that yet? No, I just found that x is 9. AC would be x plus 6. So in order to find AC, I'd have to plug in 9 for x. So 9 plus 6 will be AC, which is 15. So 15 is the length of that side. Okay, so the length of this side is 15. Just for fun, what's the length of this side? It will be 9 plus 1, which would be 10. So if these are similar triangles, the scale factor should be the same. So is 32 divided by 10, that scale factor to get from here to here, the same as 48 divided by 15? And I'm just checking this because I want to make sure that we've done this correctly. So 32 divided by 10 is 3.2. And if you plug in 48 divided by 15 to your calculator, you also get 3.2. So that means this triangle dimensions are 3.2 times the size of this one. So that is consistent scale factor. We've set this up and solved correctly. As for the reason, your reason should explain why you set up this equation. And the answer is not because you want to solve for x. That only tells me algebra. I want to know why this makes sense. And the reason why is because the ratios calculate the scale factor, and scale factors are equal. And actually, the reason you could do that is because the triangles are similar. So I might say something like, since the triangles are similar, okay, their scale factors are the same, or the scale factors between the dimensions are the same. You can say the scale factors are the same. You could also say the sides are proportional, whatever you want to say. I'm just giving you an idea. Okay, and another word for scale factor is the ratios. Ratios calculate the scale factor. Okay, you could have also said since triangles are similar, sides are proportionate in length. Okay, I'm leaving one for you to try using similar reasoning. Please pause the video and go ahead and do that. Okay, so that was a DERA problem using algebra. This one's straight up like, let's calculate some missing stuff. So you're given that the triangles are similar. Now keep in mind the order. PQS is similar to RPS. So P should be the same as R, Q should be the same as P, S should be the same as S, right, in terms of the angle. You know, these examples can be challenging when we have triangles that are nested in one another. So nested just means like they're overlapping. So what I always recommend, and you don't have to do this, but I highly recommend it, is to draw each triangle separately. So you can kind of visualize the similarities, and you can also rotate them to make it a little bit easier to see. So I'm going to draw PQS first. So PQS goes from P to Q to S. That's the bigger triangle here. So the bigger triangle looks something like this. You got P at that top angle, Q on the left, and S on the right. And we said that's similar to RPS. So before I even draw it, I'm going to, want it to look like this but smaller. So I'm going to just draw what it might look like, and I'm going to label it. So P and R should be in the same position, Q and Q and P should be in the same position, S and S should be in the same position, which makes sense because they share an angle. So P and R, that should be an R where P is. Q is in the same position as P in this case, which can be confusing because they have overlapping letters. So let's actually draw where that is on this shape here. So PQS is the big one. Its similar shape would be R to P to S. So it's kind of like on its side here. You'd have to flip it around to see that. So, now I drew R in the top, right, because it's got to be in the same orientation. And that's what makes this problem hard. Okay, so now let's go and actually identify what information we have so we can find the missing stuff. Okay, so like RP in the smaller triangle is 30. So I'm going to draw RP here is 30. So it's like flipped upside down, right? Angle R in the smaller triangle, which is up here, is 87. Okay, that's all I know about the smaller triangle. Now let's erase that and focus on the bigger triangle. So this is the bigger triangle. I know that from P to Q is 36. So P to Q is here is 36. And I know angle Q is 56. Okay, that's all I know about this triangle. Like, I don't know this angle, I don't know this angle. Even though 87 and 30 are on the inside of it, that has nothing to do with the bigger triangle. Okay, so sometimes it's helpful to separate them because now we can compare these a lot more easily. Okay, so the first thing that I know is that all similar triangles have the same angles. So P and R should be the same, Q and P should be the same. So I know angle QPS or SPQ or angle P, whatever you want to call this, has to be 87. And I know that angle Q and angle P are the same, so this has to be 56. And you can go ahead and solve for S now that you know that they have the same angles. You could find the one missing one because they're the same shape, but they're different sizes. Okay, also know, and I forgot to label this on here actually, QS here is 60. So QS is on the bigger triangle is 60. And I know that these triangles have to have the same scale factor. So like, how do I go from 36 to 30? Well, you could divide 36 by 30 to get the scale factor, and then, divide 60 the same way to get that. So I'm going to leave this problem for you to try on your own. And I'm going to come back with the answers and kind of unpack some of that. But I want you to try it first, because I feel like you know how to do a lot of this. Good luck. Okay, so there are some that you should have got just based on similarity, and there are some that were challenged. So I'm just going to go through some of the basics here. So the easiest angle to get would just be that these angles are congruent, and all triangle angles add up to 180. So if you do 56 plus 87, you get 143. And if you subtract 180 minus 143, you'll get 37. So I'll give you the measure of angle S. Actually, I guess even easier than that, RPS and QPS were, part of similar angles. So if this was 87, this was 87. So you could get, you could get QPS that way is 87. So QPS is this angle, those were the same. You get 56 because these are the same angles. Now these ones up here were, you had to add on some knowledge. So measure PQR. So PRQ was this angle here. And these two angles together make a straight angle. So all you have to do is the straight angle adds up to 180. So subtract 87, you get 93. And QPR, well, if this was 93, QPR is this angle here. And this is another small triangle. So 56 and 93. Beep, beep, beep. And whoops, I realized I just made a mistake. So let's go ahead and correct this, and hopefully you have this corrected on your paper already. So 56 and 93 will give you 149. And then since all angles in a triangle add to 180, you'll do 180 minus 149 to see how many degrees are left. And 180 minus 149 is 31. Okay, so QPR up here will be 31 degrees then. Great problem because it's practicing new stuff and old stuff. Okay, PS should have been the easiest side to find. Now, letter G and H are challenge problems, so I'm going to leave these here for you to kind of solve. I gave you some hints though. So QR, you can find QR by, so let me show you what QR is. QR is right here. You can find QR by taking, 60 and subtracting this side. Or you can find RS by taking 60 and subtracting this side. You call 60 minus X. So my hint to you is you'll have to write one in terms of the other for those two. But I do want to talk about the one that you absolutely should know, and that's how to find PS. So let's take a look at our picture. PS is this base here, okay, and it's corresponding to QS. Those are like the bases of our two triangles. In order to find those, we know that the scale factor to go from this side to this side has to be the same as the scale factor to go from this side to this side. So I set up a proportion. 36 divided by 30 will calculate the scale factor to get from this triangle to this triangle. So I went from big triangle to small triangle. And that scale factor is to be the same as if I took 60 and divided by this side, which was X, but I calculated. So that's what I set up here. 36 in the big triangle corresponds to 30 in the small triangle. 60 in the big triangle corresponds to PS in the small triangle. And then I cross multiplied and solve for PS, which I got as 50, and hopefully you did as well when you tried that on your own. So I'm leaving G and H as challenge problems for you to try. I also want you to refresh some of your skills of what we talked about last week and figure out what the scale factor of the area is and then actually calculate the area of these scaled triangles. So you may want to refer to your notes for that. But that's how you can solve different types of problems by thinking about, what similarity means, that they have the same angles, but the ratios of the side lengths are the same.